This is an interferometry setup. Basically, this utilizes a camera that is pointed at a beam splitter, and then you can see the red LED light. And so I'm just panning around. So this is the light, and the light is incident upon a mirror, which redirects the light straight vertically upwards. And there you can see a beam splitter. You can see the beam splitter here, and you can see that the light comes from the bottom and passes through the beam splitter, is transmitted through, and you can see how the camera is looking at a 90-degree angle. And basically what happens is that the light that is incident on the bottom surface of this glass prism, which has a known radius of curvature of about 103 millimeters, basically when we shine the light from the bottom, the camera is actually registering fringes that look like this, where basically the black to black fringe spacing is equivalent of half the wavelength of the light used. Here we're using a 660 nanometer red light source here from Thorlabs, and this black thing here is just catching the excess light that we don't need. We always want to minimize the light that is any stray light that is being reflected off of different surfaces. So there's some light that's actually coming through and hitting this pan, so that the light doesn't go elsewhere and cause blindness or something in other people's eyes. So we want to minimize the light that is going away. And here you can see the power of this interferometry setup. Basically, we can use this setup to measure very, very, very thin films. And so that's about it for the setup. I'm just going to pan around so that you can see the optics that are involved. Again, we use a beam splitter, a mirror, some optical posts, a camera with a long distance objective. This is at about 4 times the optical zoom. Just make sure that you use a scale bar for this for analysis.